Here we are on page 15, and we're going to be doing some rate of change, and we can do this with just basic algebra, limits with a little bit more advanced algebra, college algebra in some instances, and then we're going to be dabbling in a little bit of calculus here with the average and instantaneous velocities. And of course, when we hit continuity, we will as well. So let's start. Rate of change. Find the average rate of change. Now the rate of change, that is slope. Change in y over the change in x. So let's do it. Number one, if f of x equals this, we're going over the interval from 1 to 3. So we've got to find out, there's number one, find out what f of 1 is. And that is 3 times 1 squared minus 5 times 1. 3 minus 5 is a negative 2. And at the end of the interval, we're up at, well, let's stick in 3, and we get 3 times 3 squared minus 5 times 3. And we have 27 minus 15, that's 12. So over this interval, we rose from negative 2 to 12. So if we get the slope, well, let's look at it. We know that f of 1, we're at negative 2, and f of 3, we're way up here at 12. So this is, we don't know what the function does here. It might be a parabola, it might be a little thing. Oh yeah, it'll be an x squared, so it'll be a parabola. But we're looking for the average rate of change. So we're looking for the slope of this segment right here. So we're going to take y minus y over x minus x. And that's going to give us the average rate of change. That's just y2 minus y1 over x2 minus x1. And that gives us 14 over 2, which is 7. So this average rate of change is a 7. Number 2, we're going to go from negative 2 to 5. So we've got to stick in negative 2, see where we are. That's negative 2 squared plus negative 2 cubed. That's negative 4 minus 8. That's a negative 12 there. And what about g of 5? We get negative 5 squared plus 5 cubed. This is going to be negative 25 plus 125. What does that equal? That's positive 100. Whew! So when we do the slope is going to be y minus y over x minus x. All right, that's 112 over 7. Well, there's the slope, 112 over 7. And that could be turned into a decimal very easily. Number 3, here we have h of x equals 2x minus 19. Let's go ahead and write that down here. So we get h of, we've got to start out at 11, and we get 2 times 11 minus 19. That is 22 minus 19. That's 3. And h of 17 is 2 times 17 minus 19. That's 34 minus 19. That's 15. So the slope is going to be 15 minus 3. That's y minus y over x minus x. And we get 12 over 6. That equals 2. So we're going to have an average slope of 2. Some of you may stop right there and say, oh, wait a second. Number 3, this is y equals m x plus b. Well, yes, these have got to be the same thing. If we're actually on a line where we've got the point 11, 3 and 17, 15 or whatever that is way over there, this has the same slope all the way along. And so if we find the slope between any 2 points on there and find its average rate of change, it better be the slope. So yeah, good thing it came out to be 2, or that would have been a little bit tough. All right, let's do number 4. And we have f of 0 is sine of 0 equals 0. And what is f of pi? May have to pull back into some trigonometry. F of pi is sine of pi. On the unit circle, if you needed to review on that, is 0. So we get 0 minus 0 over pi minus 0 equals 0 over pi equals 0. The average rate of change is 0. And this would be valuable to look at this sine wave, goes look like that. And we are finding the average rate of change from there to there. And yeah, if we draw a straight line between them, that slope is indeed a 0. Good. Let's clear it off and look at the rest of them. Number 5. We have 3x squared minus 5x, and we're going over an interval that has variables this time. Doesn't matter at all. F of, let's stick in x. Well, that's what we already have, 3x squared minus 5x. And the next one is 2x. So f of 2x is going to give us 2x squared minus 5 times 2x. Ooh, what does that equal? 3 times 4, that's 12x squared minus 10x. How do we find this average rate of change? Same way, y minus y, 3x squared minus 5x. We just took this y value minus that y value over the x that we stuck in second minus the x we stuck in first. And we're still doing the exact same pattern. So what does this simplify out to? We get 12x squared minus 3x squared, that's 9x squared, minus 10x minus a minus 5, so that's plus 5, so that's minus 5x, all over 2x minus x is x. Ooh, look at this. We could factor an x out of the top and cancel. X, 9x minus 5, all over x, and those two will divide out to 1. So the answer is going to be 9x minus 5. How interesting that we now have a formula for the slope between any points that look like this in this function. It's kind of fascinating. Number 6. G of x. So we're going to stick in x first. That's a nice easy one. Negative x squared plus x. Good. And now we're going to stick in x plus 1. Negative, x plus 1 squared plus x plus 1. Alrighty. What does that equal there? This is negative x squared plus 2x plus 1 plus the x plus 1. Those parentheses aren't doing much. And then that goes in negative x squared minus 2x minus 1 plus x plus 1. And those cancel. And it equals negative x squared minus an x. Okay, so when we stick in x plus 1 into the function, this becomes the function right here. Okay, so let's try and find that average rate of change then. So y minus y, so negative x squared minus x minus negative x squared plus x all over x plus 1 minus x. So we took y minus y over x minus x. And now we get negative x squared plus x squared is gone. Negative x minus a minus x, that's negative 2x over 1. So we get negative 2x. Huh. So let's plug it right there. Negative 2x. Fascinating. Number 7. H of x. We're going to stick in a first. We're going to do this interval here. That's kind of interesting. H of a equals 13a plus 11. And h of b equals 13b plus 11. Now, this one looks like number 3. We better end up with 13 as our answer no matter what interval we use it over. Let's see if that actually comes out. So y minus y over, over x minus x. Y minus y over x minus x. Good. So we jump that in. The 11 minus the 11's there, and we get 13b minus 13a all over b minus a. Yeah, we can factor that 13 out of the top, b minus a over b minus a, and look at what goes away. And we're left with the number 13. Indeed, that's correct. Cool. It worked. Number 8. We have f of, it looks like we're starting at pi. So cosine of pi, that we'll need to review the unit circle on. Cosine of pi is -1. And then f of x is cosine of x. So we have cosine of x minus the -1 all over x minus pi. And cosine of x plus 1 over x minus pi. I'm not seeing a lot of simplification going on here. So that is our average rate of change. Cosine of x plus 1 all over x minus pi. And really what's going on here is cosine is another one of those functions that oscillates. Goes like that. And we are here at pi, and we're going to a random point x. And so you'll notice here's our -1, and if we point x on the curve going up to there, that this, depending on what x value we stick in, we could have a slope down there or a slope 0, and it will always do that. So it'll keep oscillating along with the cosine function, the average rate of change or slope of the segment connecting the dots. So that one doesn't simplify down too much. Okay, let's look at the next ones. This next set of problem is going to be with limits. Now some of you may have had very little introduction to limits, and so we're going to try to have these exercises build up the idea of a limit as opposed to a value at the function. For example, here it says find the values and limits of the following functions at the given values. So we have a function here that's split up. For some numbers we do one function, and for other numbers we do another function. We put those together. As long as these two domains don't overlap, it is still considered a function. So we're going to find out what happens when we stick in 3 and 4, and you'll see we're going to be at 7. And then what happens is that where we're getting close to with this other function. So let's look at it and see if we can make sense of it. Number 9. So it says we've got the line x plus 3 for everything but 4 specific points. So I'm going to graph the line x plus 3, y equals x plus 3. So we're up here at 3 and a slope of 1. So it's going to head off that way and then that way, like that. Now, that happens for all except a few special points where x is at -2, so that has a space right there. At 1, there's a space right there. At 3, there's a space right here. And at 4, there's a space right there. So there are spaces right along there, little breaks in the line, and it says at those values, at -2, we're actually up at 7. Oh, let me get that pencil and make that mark. We're up at 7 right there. It also says we're up at 7 for x being 1. So right there. And then at x is 3, we're up there. And at x is 4, we're up there. Yeah, and so that's our function. We're going along just fine on a line, except for where x is -2. It says when you stick in -2, you actually get 7. So the function values, if we do f of 3, particularly at this value, we get 7. It tells us right there, if we stick in 3, we get 7. So f of 4, we get 7. That's what it says right there. So but as we look at it, everything close to it, like when we stick in 2.99999, we're right here at this, getting closer and closer to this break. So the question is, what limit, what would we like to be right there to make this thing smooth and connected all the way through? And so if we were to stick in 3 up here in this top function, we would get 3 plus 3 is 6. So we write that as the limit as x approaches 3. In this particular function, we can tell, because this is a nice smooth line, of f of x equals a 6. So the limit and the function value aren't the same, and you can see the difference between the red dot and the purple dot. The purple dot is what the limit is, but it's not actually a value of the function. This function was arranged so that 3 gives us a totally different number. That's kind of weird. Why would they do that? I don't know, probably to teach you about limits. So let's see about the limit as x approaches 4. The limit as x approaches 4 of f of x. So let's do the same thing. Let's stick 4 in, even though its real value is 7, let's stick it up here. And we get 4 plus 3 is, oh my word, 7. This limit, that red dot, the purple dot, and the actual value, the red dot, are the exact same dot. The limit and the function value equal each other. So I'm going to draw a little connection right there. This is when you get this statement. At 4, this is continuous. At 3, it is not. There's a break in the line. That's an actual space in the line. The limit is there, but the value is somewhere else. So it broke the continuity of that function. Ah, good. That was a good exercise. Let's see if we can do the same thing with number 10. Number 10, it says x squared plus 3 for everything but these 4 values. So we're going to graph a normal x squared plus 3. So we're going to be 1, 2, 3 up. And it's a parabola that shoots off like this. And that's true for everything except some specific values. At negative 3, we are at negative 3, there's a break. And at negative 1, there's a break. And when's the next break? 2. So that'll be up about right there. And 4. So there's a big break way up there high. I've drawn it a little bit out of scale, but I think you'll be able to see that. So when we do this with the actual values there, you'll notice that we have 7 again. I don't know why 7's so cool. It's up about, I don't know, this high, somewhere in here. So at negative 3, we're up at 7. At negative 1, we're up at 7. At 2, we're up at 7, and that's going to be the question right there. Did we actually fill that hole, or are we off a little bit? And then out at 4, we're up at 7. All right, so the actual function values at negative 1, f of negative 1, it tells us for x equals negative 1, it's 7. And for f of 2, it is, yep, indeed 7. So those are interesting because they're interesting. They're unusual. Everything else is somewhere on this path where it's already nice and smooth. So let's do the limits and find out what happens. The limit as x approaches negative 1. So as we get closer and closer to negative 1, we're on this curve. So what would we like this hole to be? I don't think it's going to be 7. Let's try. F of x equals, stick in negative 1 here, and you get negative 1 squared is 1 plus 3 is 4. Notice that this limit, 4, where the purple circle would have been, that's what we would have liked it to be, and 7, they're different. So this is not continuous. There is indeed a break there. And then we have limit as x approaches 2 of f of x. And what is this going to equal? Well, we already know that f of 2 is indeed 7, but let's stick it up here and see if we were to stick in like 1.99 or 2.0001, do we get really close to 7? So stick the 2 in here. 2 squared is 4 plus 3 is indeed 7. Indeed, look at that. That circle right there is filled in by the red dot, and it's a 7, which means because the limit and the function value are the same, that this function is continuous right here at that x equals 2. Not at x equals 4, not at x equals negative 1, not at x equals 3. Whoever made this up, that crazy teacher, put breaks in it. They forced breaks to happen, except for right there they filled in the right hole. Good. Number 11, it's going to take a little while. May have to review a little pre-calculus to graph this guy. So let's clear this off and get some space. All right, number 11. So you'll notice that this is a rational function for x does not equal negative 2, negative 1, 3, and 7. And for when those values happen, we're at 2. And so we're going to look at these values in particular, 3 and 7, to see what happens there. Okay, let's see if we remember how to graph these sorts of things. With rational functions, there are certain keys to help you sketch the graph of them. Find out where the vertical asymptotes are, find out where the horizontal asymptotes are, find out where the x-intercepts are, and find out where the y-intercept is. So the vertical asymptotes, we better write this over here. In factored form, the numerator is x plus 7 times x minus 7. And the denominator is x minus 7, x plus 2. So, vertical asymptote happens when the bottom is 0. So that's x equals 7 and x equals a negative 2. So what that would mean on our graph is that x is negative 2 has a dashed line down here, and so does x equals 7. There's a dashed line right there. Now they are not part of our domain. We actually can't stick 7 and negative 2 into this function, which is part of the reason we have a 7 down here and a negative 2 down here. We have to fill in those holes if we want it to be defined for those values at all. Horizontal asymptote, we stick in really big numbers, like really big, like a billion. And here we have a billion plus 7, which is roughly a billion. We're finding where we're getting close to, times a billion. Over on the bottom, we're going to get a billion times a billion. Now there are some other numbers here and other numbers here, but really we're getting closer and closer to the number 1 when we stick that in. So this is an asymptote that is horizontal, meaning the arrows are going to come right out here along this line and right out here along this line. So y equals 1. The x-intercepts, what would turn this entire function 0? Well, a fraction is 0 when the top is 0. So we only have to look at when the top is 0, and we get negative 7, 0, and 7, 0. Now at this point you might be wondering, wait a second. Well, let's put them on and then we can wonder. We get negative 7, 0, so it's going to be somewhere out here, and 7, 0. And that should bother you. Yeah, now you can start to wonder. You're like, wait a second. This guy right here says that we cannot stick 7 in, otherwise we blow up to infinity. And this guy says, hey, wait a second. If you stick 7 in, we'll get 0. That's right. These guys completely obliterate each other. They're gone. And this is what it looks like algebraically. Kaboosh, kaboosh. Those guys are gone. The function is really this, except for at the value of 7, where we have a little hole. And so I'm going to show you that on the graphing calculator. So this guy, actually, I'm going to erase this little line right here. We're going to you'll see a little bit of, I'm going to leave a little bit of a remnant there so you can see he used to be there, but he just got obliterated. 0 and infinity just took each other out. That was a massive battle over there. Okay, and then the y-intercept happens when we stick in 0, what comes out for x. And this has been from time immemorial. If you put it over here, stick in 0 on the top and 0 on the bottom, we get negative, let's write this, f of 0 is negative 49 over negative 14. Divide top and bottom by negative 7, and we get 7 halves. Notice we could have also stuck 0 in right here, 0 plus 7 and 0 plus 2, 7 over 2. So we're up about right there. And with this, we can now see the graph. This guy's coming out here and getting closer and closer to 1. And it comes down through, hits the intercept, so it's now negative. So as we approach x equals negative 2, we either have to shoot up the asymptote or down the asymptote. In order to shoot up the asymptote, we would need another intercept. We don't have one, so we must be shooting down negative. That means on the other side of the asymptote, being a normal asymptote, we're going to be shooting up, and this is what it means to blow up at x equals negative 2, a vertical asymptote. And this guy comes out here and goes like that. The only issue is, and what we did last time, is that 7 is off limits, and that is there is a hole right there. Let's put this on the calculator and make sure we have done this correctly. You'll notice that I have already put this problem in like that, and so when we look at a graph, you see, oh, see here we come over here, clear out at negative 7, it's headed off, and it's going to get closer and closer to 1. And here's this guy, and then this guy coming up here. Now, a couple of things that you need to know about your calculator. First of all, if I hit this trace button, you'll notice that as I move, all the x values that are being put in are these crazy looking decimals. They're not exactly like 0.6, 0.9, 0.2. Something that you are able to do is you can actually zoom 4 zooms into the right window so that now watch what happens when I do a trace. You see these decimals that it is putting in? So if we look at the window, that's something you should note, that if you're ever on multiples of 4.7, so I'm going to zoom out just a little bit so we can still have decimals and see what they are. See here you're coming over and headed about 1, there you're coming over about 1. So let's change the window just a little bit so we can see a little bit more. Instead of going so far out to x, the interesting number is 7, so we want to, how about negative 9.4 and 9.4. That'll allow us to see everything, but we'll still be on that multiple of the window to allow decimals. And let's see what the graph looks like now. Ah, there we have it. You'll notice what happened. You see that little break that I drew over here? The graphing calculator finally stuck in exactly 7, and it didn't know what to do with it. It couldn't do anything. Let's go to the table to make sure we see what's going on there. As you look right here, you'll notice that these numbers, as we shoot off to negative infinity, these numbers are getting closer and closer to the number 1. That's the horizontal asymptote coming out. So let's get back up into the normal numbers here, and we're coming up, and you'll notice we hit negative. At negative 7 we hit a 0, that's an intercept, and then as we keep putting in negatives further up, we're headed negative, and it shoots down to negative infinity right up until we hit negative 2. It has no idea what to do with that, and then it goes, shoots up to positive infinity, comes down, and at 0 it's at, oh, look at that, 3.5, 7 halves, good. Right up until it hits 7, and again, it has no idea what to do with 7. So, yeah, it leaves a blank. So that's what the graph is. So yeah, what we've graphed here is actually what the calculator does, but sometimes it takes a little manipulation of this technological wonder to get it to get you to see what is actually going on. Good. So let's resume back. We've got it graphed here. That's the top one. Now we have to actually do what it says here. For negative 2, good. Yeah, we know we can't be on that one. For negative 1, we've got to erase right above negative 1. Okay. Can't above 3, so somewhere like right there. And above 7. Yeah, we already have that one. So now we need to find out the actual values at those points. So right here, the actual value here is 2. So at negative 1, we're at 2, probably about right there. At negative 2, we're at 2. And at 3, we're at 2. Ooh, that looks like that might fill the hole. That looks like we're a little bit tall. So let's check it. Now notice that this function is defined for every number on the entire number line. Even things that we couldn't have before in this function, yeah, it's now defined for those numbers. And so it's kind of hopping all around and bouncing and asymptotes and values and all sorts of stuff. So at x equals 3, let's see, what do we have? If we stick in x equals 3, yeah, f of 3 is indeed 2. And at x equals 7, of course, f of 7 is 2, because we made it so. We didn't know what it was before. In fact, it wasn't anything. And at negative 2, it's a 2. So let's do the limits and see if we fill some of these holes. So the limit as x approaches 3. Now, if we stick in 3 up here, notice we could do 3 plus 7 over 3 plus 2. That's 10 over 5. Yeah, if we stick that in, we get 10 over 5 is 2. Or we could actually stick it in to the big one, and let's do that. X plus 7 is 10 times x minus 7 is negative 4 over 3 minus 7 is negative 4, and 3 plus 2 is a 5. This is negative 40 over negative 20. It's negative 2. Yeah, see those numbers just cancel? It happens like that all the time except for at the number 7, which that's why we don't have anything. So yeah, if we were to go back to this and look at the table, let's go to that table and notice what the value of 3 is at the function if we had not defined it for that. Yeah, that's the hole. So right there. So this guy does indeed fill that hole, and it will be continuous at x equals 3. Now let's do at x equals 7. The limit as x approaches 7 of f of x. And this guy is going to be, notice we can't stick in this one. We'll get 0 over 0. So we have to find the limit, since for everything else it works to cross those two out. So 7 plus 7 is 14 over 7 plus 2 is 9, is 14 ninths. So that's like 1.555555. And if we look here, yeah, 7 can't be stuck in here, but you'll notice we're right about 1.55555. And if you were to stick in numbers closer and closer to 7, you'd find that that's what it got closer and closer to. This is the standard way of finding limits at the end of pre-calculus or at the beginning of calculus, is you factor everything and cancel out the ones that are bad, the ones that cause problems pathologically, and then just stick them in to the other one. It doesn't give you the actual function value, but it gives you what it would be or what it is getting very, very close to. So cool. It is continuous at x equals 3. Good. Number 12. On this one, it's a little bit different. We have whole intervals that this is defined for. So 2x minus 3. So let's go here. We're down at negative 3. And then we go up 2 over 1. So we've got a pretty steep line going like that. But we note that this is only defined for x is less than 3. So up here, 3, about right here, this is actually not defined there. It's only for x is less than 3. So I'm going to put a little circle here just to make sure we know what's going on, that this is not actually part of the function. So at 3, we go right up to it, but we don't include sticking in 3. All right, now let's try the next one, negative 2/3 x plus 6. So this guy would be up at 6 and then down 2 over 3. So like right there. So this one looks like this, but this line, we're only on this line for x is greater than or equal to 3. So I have to erase everything from here this way. Let's see if I can get that. Yeah, there we go. And this one actually has a solid dot. Okay. So the question is, did we fill the hole? So we're all continuous here. Of course we're going to be continuous there, and we're going to be continuous there. So at x equals 0, let's look at that. What's our actual function value? Well, f of 0, 0 is less than 3, so we stick it in here. 2 times 0 minus 3 is indeed minus 3. Yeah, we have that. F of 0 is minus 3. Now, at 3, f of 3, if we stick it in, we're in this category right here, so we've got to stick it in here. Negative 2/3 times 3 is negative 2, plus 6 is 4. So yeah, you'll notice that solid dot is actually up at 4 right there. Now, the limit, you'll notice that this is a nice smooth function heading this way. So the limit as x is approaching 3 from this side equals 4. But from this side, notice that it's different. It wants to go to, what if we stuck 3 in for this other guy? 2 times 3 is 6, minus 3 is 3. So here it's shooting for 3, and here it's shooting for 4. This limit, let's write that limit as x approaches 0. Oh yeah, we stuck that in, and that was a nice smooth area, and it's negative 3. So good. These two, it is continuous at x equals 0. That was like almost a no-brainer. But the other cool one, limit as x approaches 3 of f of x. Yeah, from one side we're getting closer and closer to 4, and the other side we're getting closer and closer to 3, and the actual value is up here at 4. There is no limit. So it can't be continuous. The limit has to be the same thing from both sides, and you have to fill a hole. This is not continuous, and the limit doesn't even exist at x equals 3. Cool. Next one. Whoa, we're going to need some space. This guy has 3 different functions over 3 different intervals. All right, number 13. Let's see what we can get here. So we've got negative x squared minus 5x. So let's graph this kind of big. Negative x squared minus 5x, that's like having 0 and negative 5 as zeros, negative 5 halves up here. So it's going to be a parabola like this. Wow. Okay, so that's negative x squared plus 5x. Okay, good. But that's only for x is less than negative 2. So I got to do a little bit of erasing here to find out, to be able to get this. So go to where x is negative 2, and it's about like right here. We are only on that parabola for this much of the domain. In fact, I'm going to highlight that right here in this color, this orange, so we can see that. So only from negative 2 backwards. That vertex is at like negative 2.5. So good. And do we stick in negative 2? Nope. So this is a circle right up here. All right. And what happens if we actually stick it in? Let's just find out how high it is up there, even though it's not actually the value. Negative 2 is, so we get negative 4 plus 10. That's a 6. So this guy up here is at height 6. That's where that open circle is, even though it's not part of the function. All right, let's look at the next one. 1/2 x plus 5. So if we're up at 5 and we go 1/2 x. So up at 5 and we go about like this. There we go. Now we've got to cut it down to where it really is, just from negative 2 up to 4. So there we go. And up to about, let's mark that at 4, however far 4 is up here. There we go. Now let's put that on, and right like that. Good. So it says that we're at from negative 2 up to 4, and we include both of them. So here's a solid dot right here on the end. There we go. And there's a solid dot right there on the end. So the value of negative 2 is negative 1 plus 5. That's a 4 up here. So this guy is at height 4. And how big is it over there? If we stick in 4, we get 1/2 times 4 is 2 plus 5 is 7. So this guy up here is at 7. I'm going to mark it over there, but it's at 7. All right, now let's look at the last one. X squared minus 8x plus 25. Oh boy, what does this guy look like? This looks like a vertex at 4. Stick in 4, so right up here. So it's going to be a parabola headed up. I don't know where yet, but if we stick in 4, that's 16 minus 32 is negative 16 plus 25. So 16 minus 32 is a negative 16 plus 25, that's 9. So we're up here at 9 like that, and heading up at a parabola like that. And the other side, that's not what we are. So this is a really funky looking problem. Look at that guy. So the question is, at x equals 2, what is the value? And so let's do this. F of negative 2 is this guy right here. where it equals negative 2. So this is 1/2 times negative 2. That's a negative 1 plus 5 equals 4. And f of 4 is again right up here. We don't stick it in this one. So the actual value at 4, we did that before. 1/2 times 4 is 2, plus 5 is 7. So those are the values. What about the limits? Well, the limit as x approaches negative 2 does not exist. You can see we're headed to 6 from the left, and we're headed to negative 4 from the right. And so that one does not exist. What about the limit as x approaches 4? Well, sure, you can see we're not going to make it. We get closer and closer to 7 on this function, and this guy heads off from 9 and heads up. So that guy doesn't have a limit. So we are not continuous at negative 2 or 4. Now, if we had done this like negative 1/2 x plus 5, and it went like this, man, that dot would have been right on there, and we would have had a continuous function at negative 2. Certainly it's continuous at all these other values, but at these breakpoints, we didn't match up, so we're not continuous. Good, that was limits from number 9 to number 13. Good.